This video, I want to take a look at a couple of models and applications of higher order differential equations in the context of boundary value problems instead of initial value problems. And the first one I want to look at is an application related to civil engineering, and that is beam deflection. So basically, the idea behind beam deflection, when I talk about a beam, literally like a beam that you would use as a structural element in a house to support the ceiling, basically just a big horizontal piece of either wood or metal or whatever the material may be that's meant to support something above it. So in this case, we're going to be talking about a uniform beam, so its idea is that it's basically the same thickness, same strength uniformly across the entire beam with no load on it. So there's nothing weighing down on it. So a uniform beam with no load, and that includes the weight of itself. So hypothetically, this is a ideal beam where it doesn't even have its own weight. It is a weightless beam. Including its own weight, and then we'll add some weight to it, but sort of ideal, not necessarily realistic here. And let's say that it is attached to maybe a wall or something at two ends. So the idea is that maybe we have some walls of some sort, and the beam runs horizontally between these two walls. Let me try to clean this up, make this picture a little nicer. So there's no load on the beam, so it's perfectly horizontal. And we'll use sort of the center line of the beam to be known as what is called the axis of symmetry. So this center line right here is the axis of symmetry. Well, what happens to this beam when we do apply a load? If we apply a load to this beam, so now we are going to apply a load, it will bend, it will deform. And it'll deform basically in this particular way. It'll look roughly like this. And you can think about what's happening to the center line as kind of being the thing that we're keeping track of. So this center line, what that used to be the axis of symmetry, is now going to be our deflection curve. And obviously, realistically, if your beam is bending this much, you probably haven't appropriately sized your beam, and you're going to be in trouble if it starts to deform that much. But it turns out that this situation, calculating beam loads, can be done using differential equations. And it's related to a bunch of very physicsy stuff that if you go into civil engineering or structural engineering of any sort, you'll learn a ton about. I barely know the first thing about it, so I'll just give you the basic, quick, and dirty rundown of all of this. So there's something called a bending moment. And a bending moment, so the bending moment, which we're going to treat as capital M, or call capital M, is related to essentially the pressure that's being put onto the beam. So the load per unit length. And that unit length, or that load per length, we'll maybe use W for like weight, and it could be a function of X. So sometimes all of that force will be applied at a single point right in the center. Maybe it's applied totally uniformly across the entire beam. But the bending moment is basically what you can think of as a force. So when we talk about moments, they're always related to the idea of a force that's being applied onto the beam. Sometimes they're, when we talk about moments, they're in the context of like a rotational sense. So like torque is often referred to as like the first moment of force in a rotational frame of reference. So if you don't know what a bending moment is, I'm not going to be able to give you a very good explanation other than it's essentially analogous to a force. And it turns out that in this case, the bending moment M is related to the load per unit length W by the following. And I guess I don't need a comma there, so by the following. The derivative, in fact, in this case, the second derivative of the bending moment with respect to position is equal to this load function, load per unit length. And it turns out that this bending moment is also proportional to the curvature of this deflection curve. So when we look at the deflection curve up here and see the shape that it's taking, it turns out, M is also proportional, so we're going to be able to redefine it here in a minute, also proportional to the curvature, of the deflection curve. If you haven't dealt with curvature before, you can think of curvature as sort of like it's a measurement that tells you how curved something is. It has units of inverse length, so like sort of 1 over the radius. If you imagine this curve up here extending and making like a big circle, then the radius of that circle would be related to the curvature. So the more curved it is, something that's really, really curved is going to make kind of a tiny circle, whereas something that's barely curved will have a really large circle with a large radius. And so curvature is the reciprocal of that radius of curvature. So down here, let's keep going with this. Turns out it's proportional to the curvature, the curve of deflection, which we will use the letter, when we talk about curvature, usually the Greek letter kappa is used. It kind of looks like a little K that's a little squiggly. And it's done in such a way that our bending moment is equal to E times I times the curvature, where E and I are respectively the Young's modulus and the moment of inertia of a cross-section of the beam. So again, a bunch of technical stuff that we don't really care about yet. I just want to get to the math. But where E is the Young's modulus, so it just has to do with properties of basically rigidity properties of the beam, how stiff the beam is. And I is the moment of inertia which is again going to be a topic that's kind of related to, in a sense, kind of related to torque of a cross-section of the beam, so to speak. So, and it turns out this is about an axis called the neutral axis. If you want a better explanation of any of this, definitely go find a civil engineer instead of a mathematician to talk to about this stuff. But basically, for all intents and purposes, these two things are going to be constants. So from a mathematical standpoint, we don't care. These two things are constants. But our moment, up here, our bending moment is essentially going to be proportional to the curvature of this deflection. And I'll define the curvature in just a minute. Okay, So this term, the E and the I together, when you multiply them, it gives you something called flexural rigidity, which is something that hopefully you have some intuition for. It's just literally kind of a measure of how rigid is something, how stiff is it, how hard is it to bend that material. The kappa term, our curvature down here, has a mathematical formula. And the formula for this is essentially y double prime over 1 plus y prime, in parentheses, squared, whole thing raised to the 3/2. This is a formula that you will encounter or have encountered in one of your calculus courses. It definitely comes up, I believe, a little bit in Calc 3, and you may have even seen it in one of the earlier calculus classes, possibly even Calc 1, depending on what your instructor happened to cover. But this is a formula that will be more explained. You can go look up curvature in your old calculus book, and they will actually derive kind of where this formula comes from and give it a little bit of an explanation. But for us, we're going to assume that the curve that we're dealing with, the beam that we're dealing with, isn't deflecting that much. If your beam really starts to deflect, then basically it's only a matter of time before it fails entirely. So we only want to deal with beams that are very slightly deflected. And if they're only very, very slightly deflected, in a sense, you can think of y being sort of the equation. So y is the equation or the function, or curve, I should say. That's a better. Y is the curve we're measuring. So what I'm suggesting is, in this picture up here, right, this is our curve, basically, like y equals whatever, y equals some y of x. So this deflection curve is the y that we're talking about. So in this case, if that curve is essentially flat, if it's essentially horizontal, if it looks more like this, what that tells us is if it's almost flat, so if the deflection is very small, meaning y is essentially flat, then what does that tell us about, for example, y prime? Well, if it's flat, then y prime is essentially 0, right? The slope is going to be close to 0 the whole way across, right? When it's a flat horizontal line, slope is almost 0. And if the slope is almost 0, then this term down here in the denominator is almost 0. We have this plus 1 over here. The whole denominator essentially just becomes the number 1. So the whole denominator is 1. So the denominator of our curvature is about 1, which tells us that the curvature is essentially the same thing as just y double prime. Okay, so putting all of this together, we have the following. We have that our value of m, which we said was EI times the curvature, is now approximately EI times y double prime. So our bending moment, we now have an expression in terms of y, the shape of this deflection curve, and we can plug this expression into this equation up here to get the following. So this is going to give us that basically our d squared m dx squared, which was supposed to be equal to w, that whole thing is going to become now the derivative of this EIY double prime term with respect to x is equal to w. And the e and the I are just a constant that we can pull out. And we have the second derivative of y double prime. So we already have taken two derivatives of y. We're now taking two more derivatives, and we wind up with a fourth derivative equal to our w. And again, w is a function of x. So this is the differential equation that we can use. And the point is, it's a fourth order differential equation. This isn't something that we're going to do a ton of problems related to this. It's just kind of, again, I want to introduce some of the conceptual ideas related to this. This is probably not something you need to worry about on exams, just trying to give you a little exposure to some of these other topics. Okay. Because it's a fourth order ODE, that means that we need, I don't know, I did a dot, dot, dot there. We need four conditions, right? To solve a fourth order differential equation essentially involves four integrals and four constants of integration. So we wind up with four unknown constants that we'll have to prescribe the values of, and to prescribe those values, we'll need four conditions. So typically, there are three, so there's a bunch of different ways that you can prescribe these four conditions. And in this case, they're going to be boundary conditions. But there's three common cases. So three common situations. Okay, so let's imagine, case number one. So in the first case, we're going to actually embed the beam in the two walls that are on the side. So imagine these are the walls, they're solid objects over here. And the beam actually goes into the wall. So it sticks into the wall here, it sticks into the wall here. I'm going to just draw it as a line as opposed to like trying to draw an actual three-dimensional beam here. We'll just use a line. But it goes in. That means when it comes out of the walls, it's going straight, and then it's going to dip down a little bit due to the deflection, due to whatever load, and I'm kind of drawing this in hopefully an exaggerated way. And then it comes back up and goes back into the wall at the other side. So there's kind of what the deflection will look like. It's embedded into the sidewall. So this case is an embedded case. And so if we call this 0 and this L in terms of x, right, our x-axis, so basically if you want to think about it this way, right, here's our little x and y directions for this thing. So here's 0 on the x-axis, here's L, a length L on the x-axis, and we're going to keep track of the height of the deflection of the beam. So that is our equation y. The four conditions in this case are going to look like the following. Condition number one is that it is stuck into the wall on the left. So let's say that basically we're putting our origin right here. This is where I'm putting my origin. So this right here is the origin. So this tells me that y of 0 is 0. Basically, this beam goes through the origin. But it also goes through, if my x-axis is going out horizontally here, it also has to go through the point L, 0. So basically, we've prescribed the height of the beam at the two ends, at 0 and L. So basically, in this case, in fact, let me reorder these slightly. Oops, come on. I'm going to actually do the second one down here just to make this a little easier and cleaner going forward. But basically, stuck into left wall, and this one tells us that it's stuck into the right wall. So it's stuck into both walls at both ends. The next one is going to be related to the derivative at both of these points. And in this case, the derivative is 0 because, again, it's stuck into the wall. So at that exact point, the beam is coming out horizontally, right? There's no load on it yet to start to deflect it downward until you move to some positive x value. And same thing over here at the L. Going into the wall, if it's stuck horizontally into the wall, right when it leaves the wall, it's still horizontal. It may start to deflect immediately after that. But basically, because it's stuck into the wall, it comes straight out from the wall on both sides. So both of these are also 0. So straight out from the wall. And so essentially these two down here are the same two reasons. Also because it's straight out from the wall. So I just want us to understand, like, between looking at the picture and understanding how that relates to these conditions. So this is one common case where it's embedded into the two walls. One other possible and very common case is where you're basically treating it as sort of a cantilever. So you have it, we only have one wall here, and it's totally free. So I'll use a dotted line because there's no actual wall over here. But basically you have it come out of the wall on the left, but then it's not attached to the wall on the right, so it can start to deflect. Draw this a little better. Okay, good enough. So this is the idea, and it comes down essentially to that same distance, L and 0 here. So sort of the same setup. We're treating this point as our origin right here. So here's our origin. And in this case, the boundary conditions on the left match the boundary conditions up here, right? It's coming out of the wall. It's fixed to this given height coming out of the wall, and its slope as it leaves the wall is also going to be 0. So the first two conditions over here match the first two conditions that we had before. So y of 0 equals 0, and y prime of 0 equals 0. So these match the previous versions of number 1 and 2. But what about equations 3 and 4? Well, I can't apply anything about what's really going on at L in quite the same way, other than to say, right, I can't specify the height. I don't know where the height of this is going to be because it's deflecting some amount, so I know it's going to be lower, but I can't prescribe what the value of y is at position L. And the other thing I can't do is I can't tell us what the slope is here. So I don't know what the slope is here. So imagine we're trying to basically figure out over here. Here's, if it had come straight, it would have hit right here. We'd know the height. We'd know that it was horizontal. But because it started to deflect downward, it's down at some other point. I don't know how low it went. And because it's also tilting down, I also don't know the slope at that point. So I can't prescribe either of these conditions on the right-hand side. So instead, what we do know is that basically at this very edge, there's no load any further to the right of it. So basically when you get all the way out to L, so when we go all the way out to position L, the curvature is 0, meaning the second derivative is 0. So basically what I'm suggesting is if there's no load as it tilts downward here because there's no extra weight on anywhere to the right of it, it's going to be essentially instantaneously, if you kind of zoomed in here, it would look like a straight line. It's not instantaneously curving any more than that downward. Hopefully that kind of makes sense. But basically the far right point, there is no curvature to it. It flattens out because there's no additional weight. All these other points, you can think of it as sort of weight to the right, weight to the left, and therefore it's being kind of curved. But on this one, there's only weight to the left, there is no weight to the right, and so you can think sort of instantaneously at that point, it has stopped curving. It's kind of, the curvature is leveling off. So basically, the way that we say this is, oops, not that one, I need the pen. This one, the bending moment is zero. It's uncurved at that endpoint. Right, so it's uncurved at the endpoint. And the last one looks like this. It's going to be that y triple prime of L is equal to 0. And this has to do with what's called the shear force. In this case, the shear force is 0 as well. So it turns out that's the condition that you would, these are the boundary conditions you'd use in a situation like this. The last case that's very common is more similar to the first one. The beam is being supported at both ends, but instead of being embedded into the walls, it's literally just sitting on top of something. So there's no walls in this case. Instead, you can think of it as sort of, here's a single little point that it's resting on here, a single little point that it's resting on here, and the beam is touching on those, but it's not embedded anything. It's free, essentially, to either side of this. And so, assuming that it stops right when we get to the tip on this side, right when we get to the tip on this side, and that this point right here is again going to be our origin. So here's our 0, here is L. So it's not really fixed to anything. All that's happening is it's sitting on top of a single point load right here and another single point load right here. This is the case where we call it supported. Oh yeah, let me name these other ones. So embedded, this one is what we call free support, and this one is just regular support, or supported, but not embedded into anything. So in this case, same thing, I'm going to be able to tell you what position the beam is at these 2 points. So I'm going to be able to give us, getting all of these, I'm going to be able to tell you that y of 0 is equal to 0, and I'm going to be able to tell you that y of L is equal to 0. I know the position of the beam, so we have the fixed position on the left sitting on top of that little triangle. We have a fixed position on the right sitting on top of that little triangle. But I don't know anything about what the slope looks like. But what I do know is for the same arguments that we had here at this endpoint that was free, these aren't going to be curved because there's no additional beam to the right of this one or to the left of this one that would kind of bend down on it and make the points be curved. So in this case, y double prime will be 0 and y double prime will be 0 on both of the endpoints. So again, same idea. It's uncurved here. So the same argument, the bending moment is 0. So uncurved. And so these are the types of boundary conditions you would use for all of these different situations. And there are other situations beyond these, which engineers have cleverly come up with the appropriate boundary conditions to represent, but this is the idea. Let's look at one kind of quick example of how this might bear out in an actual problem. Let's say the load that's on the beam is uniform and constant. So if the load on the beam is uniform, say a constant W0. If this is the case, then we get the following. So what I'm suggesting is basically we've got a beam and the weight pushing down on the left on every single point on the beam, it's all the same amount of weight. if all of this is what we've got, and let's say we have one where it's embedded at both ends. So let me add that as well. So the weight on the beam is uniform. It's embedded at both ends. Then our picture looks basically like this. So we've got, again, our two walls. The beam is coming through like this, and it's deflecting a little bit because there is a constant at every single point. The weight bearing down on the beam is the exact same amount, and it's an amount W0 bearing down on uniformly on this beam. Okay, what would we get if we tried to solve this? Well, our differential equation, if we go back up, is that fourth order differential equation that we specified earlier. So right here, this is the equation we're looking at. And what we're suggesting is that because the load on the beam is uniform, that's this W function here. This W function is just going to be a constant. It isn't dependent on x. It's the same at all points. So we have EI d to the fourth y dx to the fourth equals a constant, which is W0. And because it's embedded at both ends, our conditions are that y of 0 equals y of L, which equals 0. So again, same thing. We're kind of saying that origin is right here. There's our origin. So we have a fixed position of the two endpoints, and we also have fixed slope at the two endpoints. So it's coming straight out of the wall at both sides. So there's our boundary conditions. So here's our equation, and here are our 4 boundary conditions. In this case, it's really simple because this differential equation, this is a constant, these are constants, so we really just have dy dx, the fourth derivative, d4y dx to the fourth, is equal to a constant. The fourth derivative is equal to a constant. So this equation just becomes fourth derivative of y with respect to x equals the constant w0 over ei. How do we solve this? This has basically already been separated for us. So even though we don't have techniques that we've necessarily used on this, I mean, we essentially could, but the easiest way is just going to be integrate 4 times. We can treat this like the first order equation. So it's a separable one, and we'll integrate it and get another separable one, and integrate it again and get another separable one. But basically what we would get in integrating this is the following. If we're integrating a constant, after integrating it once, it'll become a linear function. After we integrate it twice, it'll become a quadratic. After we integrate it 3 times, it'll become a cubic. After we integrate it 4 times, we will have a quartic here. And so the solution will be, we'll get that y is equal to some constant c1 plus some other constant c2 times x plus some other constant c3 times x squared plus some other constant c4 times x cubed plus, this is the term that will have been integrated all 4 times, so this coefficient will survive all the way through basically. And if you think about the coefficients that will pick up along the way, we will get W0 over 24 EI times x to the fourth. So where did this coefficient come from? Where did I get this? Basically, think about integrating it once. We'd go from W0 over EI. After we integrate it once, we'll get W0 over EI times x. After we integrate that twice, we'll get W0 over EI, and the x will integrate to a 1/2 x squared, so we'll have an x squared, but we'll have a factor of 2 down here. After we integrate the 3rd time, we'll have our W0, we'll have our 2EI, and when we integrate the x squared, we'll get a 1/3 x cubed, so we'll have x cubed with a factor of 3 down here. And when we integrate the 4th time, we'll have our 3 and our 2 already down here, times e times I. that x cubed will integrate to 1/4 times x to the 4th. And the 4 times 3 times 2 is what gave us the 24. So I neglected the plus c's that we picked up after each integration. Those are accounted for over here. But this one term, this coefficient, will eventually become W0 over 24 EI. So there's that piece. Here's what it integrates to. And now we have our 4 unknowns, and we plug in our 4 conditions. So plug in our conditions, y of 0 equals 0. When I plug in 0 for x, that'll kill off all these terms, and all that'll be left is C1, but it's supposed to be equal to 0, so C1 has to be equal to 0. When we plug in y prime of 0 equals 0, this term's already 0. When we take the derivative y prime, this C2 term will become a constant, and all of the other terms will still have an x in them. So all of these ones will get zeroed out because they'll all have a factor of x, but the C2 will now be a constant, and it'll be the only piece that survives. But C2 has to be equal to 0 because the only piece that survives our C2 has to be equal to 0. So again, if you have any doubts about what I'm doing here, you can literally just plug in. For this first one, plug in 0 for all the x's. We get C1 is the only thing that survives, but when we plug it in, it has to be 0, so C1 equals 0. After we take the derivative, this will be the only term that survives because this one's already 0. Right? This will be a constant. All these other terms will still have an x in them, so when we plug in x equals 0, all those other terms will get killed off, and we'll only have C2 left, but it has to be equal to 0. Then we plug in the points on the other side, so y of L equals 0 tells me that now I'm going to have the only terms that are going to be left are going to be C3 times plugging in L squared, plus C4 plugging in L will get L cubed, plus W0 over 24 EI times L to the 4th, and that whole thing has to be 0. And we'll get a big ugly expression for that. Then we'll take the derivative of that and plug in L. So take the derivative of the whole thing again. Remember, these two terms are already gone. We already killed them off. When we take the derivative, this will become 2 times C3 times L. This one will become 3 times C4 times L squared. And this last one will be 4 times omega naught over 24 EI. And that will become L to the 3rd power. Excuse me. L to the 3rd power. And that also has to be equal to 0. And so we've got our 2 unknowns here, C3 and C4, in a big, ugly system of equations. I don't want to go through the algebra, but if you do the algebra, the linear algebra required to solve for solve for C3 and solve for C4, right? We have 2 equations for those 2 unknowns. All these other parameters are supposedly given and known in the original problem. We wind up with C3 equals we get W0 L squared over 24 EI. And for C4, we'll get negative W0 L over 12 EI. And again, solving this system of equations is something that's not necessarily difficult, it's just tedious. We could do a elimination method to solve for C4, right? I could double the top equation and subtract the 2 equations, and that would give me C4. And once I know C4, we can go back and plug into either equation to solve for C3. But this is what you will wind up getting. So again, this is just an example of what can happen in these problems, the way that you would approach them. We lucked out because it was a 4th order differential equation here that was non-homogeneous, but it was also a pretty straightforward, easy one because y didn't show up as a dependency anywhere on the right-hand side. It only showed up in one place, and we could get away with strictly integrating to solve for y. Okay, so again, don't worry about this. This is not going to be something that you're going to see a ton on exams or anything like that. It's just conceptually what's going on. I want to give you a brief introduction. Let me give you an even briefer introduction to the idea of essentially electrical vibrations, right? We did the mass spring system in a sense. So let's do this one. And you could think of mass spring system as physical vibrations, essentially of a mass and spring. Let's think about this as electrical vibrations on a series circuit. So if you basically have a series circuit where you have a series of things in line with one another here, so maybe we have a capacitor with capacitance C, we have some sort of resistor over here with resistance R, we have some sort of inductor over here with inductance L, and we are basically running electricity through this circuit. If you basically account for all of these, it turns out that the equation that you wind up getting looks like this. So there's L, the inductance, times di dt. And I'm going to use lowercase I here just to hopefully kind of disambiguate, but I is basically our current. Usually, a lot of times you'll see them use capital letters for this, but I think our book uses lowercase here, so I'll just stick to what they're doing. Same thing for the next term, and the last term looks like this. And we'll talk about how these are all related. So let me just highlight what all of these are again. So L is our inductance. I is going to be current. It shows up in a couple places, so I is current. R is the resistance in a resistor. We have C. This C over here is the capacitance. And Q is charge. And if you're not very familiar with electrical stuff, current is basically charge per time. So the units of current are Q over T. So how much charge flows through a given cross-section of wire in a given amount of time. And over here on the right side, we have our induced voltage. So right, we have some sort of power source, something that's being applied to it here. So recognizing that I, the current, is equal to the rate of change of charge as a function of time, so how much charge passes through at a function of time, this gives us the following. I'm going to replace everywhere that I shows up with dq dt. And right here where we already have di dt, you can think of it as now the second derivative of q with respect to time. So we're going to have L times d squared q dt squared plus R times dq dt plus 1 over c times q equals our e of t. And this is now a second order linear non-homogeneous equation that we can solve with the techniques that we saw before. And you get the same types of behavior because there's a lot of similar properties about things being like resistance being playing essentially the role in electricity of friction, of damping, right? It tells you, you can think of it as electrical friction in a sense. This capacitance over here, it's basically how much charge can build up on this little piece of capacitor. And so they all have sort of analogous things to the spring method or the mass spring system that we talked about before. But we wind up with a second order differential equation, and we wind up getting the same types of solutions for what the charge can do. We can find the charge to oscillate, right? So second order linear constant coefficient ODE. Similar solutions. to the mass spring system. But now what's oscillating is no longer the height of or the position of the mass, but is the actual value of the amount of charge basically flowing through this circuit. So you can get oscillating charges from a setup like this, and all you have to do is basically tweak capacitance, resistance, and inductance to set up the different types of behavior that we're seeing in a mass spring system, but now related to electrical vibrations. So again, it can be done. I don't want to go into any more detail than that. It's not going to be something that shows up on exams, but it exists. The one that I do really want to focus on, so both of these examples, I just want you to be exposed to them, see that they exist, see what it looks like to prescribe 4 boundary conditions instead of only 2 like we were doing on second order equations. But this last one is one that's actually going to be used. This will show up on your homework. So neither of these previous 2 are going to be on the homework, but this last one will be. And that is eigenvalues and eigenfunctions. And later in the class, we'll talk about something called eigenvectors, but that's for another day. It's very closely related to these, but just in a slightly different context. Okay, so I want to consider one very specific equation when we talk about eigenvalues and eigenfunctions. So I want us to consider the equation given by y double prime plus lambda y equals 0. So this thing is a second order differential equation. If you tried to relate it to like a mass spring system, you'll notice there's no y prime term. So there is no, there is no damping term. We shouldn't totally relate it to a mass spring system because there's also nothing in this equation that says that this term has to be positive. This plays the sort of equivalent role of a spring constant if this were a mass spring system, but because it's not, we're allowing for this thing to be negative. The idea is equations of this form show up a lot, and so I want to get really comfortable understanding the types of behavior that we can see fall out of an equation that looks like this. If lambda is positive, if lambda is negative, and even if lambda is 0. So for any given value of this coefficient here, what type of results are you going to get? And I want to do it with the following boundary conditions. I want to prescribe that y of 0 is 0 and that y of L is 0. So we're solving this not as an initial value problem anymore. We're solving this as a boundary value problem where we are fixing the height of this curve y at the point 0 to be a height of 0, and also at the x-coordinate of L, we're fixing the height of the curve to be 0. So basically we're saying our curve has to go through these 2 points. It can do whatever else it wants to in between, as long as it satisfies this differential equation, but it's fixed at these 2 points. What types of solutions can we get out of this? Okay, so let's take a look. Are there any interesting, and by interesting I mean non-trivial solutions? So one thing is obvious. If I just let y be 0 uniformly, this will definitely be true. It'll satisfy these conditions for sure. So y equals 0 is definitely a solution. This term will go to 0. The second derivative of 0 is also 0, and we'll just have 0 equals 0, which also satisfies both of these conditions over here. So that's a trivial solution. I'm interested in non-trivial solutions, so not y equals 0. Let's look at the 3 possible cases. So the first case is, let's let lambda be equal to 0. So I want to look at the first case, so 3 cases, lambda greater than 0, equal to 0, and less than 0. And let's start with the lambda equals 0 case. So case number 1, lambda equals 0. If lambda equals 0, then our differential equation can be written as simply y double prime equals 0. And we've got these conditions over here, y of 0 equals 0, y of L equals 0. So here's the differential equation that we are now solving, if this is true. If we're solving this equation, it's simple enough because there's nothing on the right-hand side. It's an easy differential equation to solve because it's just y double prime equals a constant, and in this case the constant is 0. So what happens, we can just integrate twice, both sides. After I integrate this once, I'll wind up with a constant over here. After I integrate that, I'll have a linear term over here. So after integrating twice, we'll wind up with y equals c1 plus, or maybe we could call it c2 plus c1x, however you want to call it. Yeah, it doesn't matter which we call them. Let me just do them in order. So c1 plus c2x. This is what you get when you integrate 0 twice. You integrate it once, you'll get a constant. When you integrate that constant, you'll get the constant times x plus some new constant. So here's the result of integrating it. Now let's apply the conditions. Apply the boundary conditions. So the first one says that y of 0 equals 0, which implies when I plug this in, we'll get c1 plus c2 times 0 equals 0. Well, the c2 times 0 kills off this term, and that means that the c1 term has to be equal to 0. And when we plug in the other one, y of L equals 0, all that's left is c2 times L now, but that has to be equal to 0. The L certainly isn't 0. We're presuming that there is indeed some length that we're solving this over. So L has to be a non-zero value. So that means that in this case, c2 has to be 0. And so in this case, the only solution is the trivial solution. So y equals 0. 0 is the only solution, and it's a trivial solution. So that's not a very interesting case. Let's look at other possibilities. Case number 2. I want to look at what happens if lambda is less than 0. So if lambda is less than 0, I'm going to rewrite this differential equation, knowing that this term has to be negative. Let me make it totally explicit that it's negative. I'm going to do that by doing this. Y double prime minus alpha squared y equals 0. And again, I'm having the same conditions that y of 0 equals 0, y of L equals 0. So there's my conditions in this case. But lambda is equal to negative alpha squared. Right? I'm forcing lambda to be a negative thing because no matter what I pick for alpha, it'll be squared and that'll be positive, and then the negative sign will force this term to be negative, which will ensure that, again, the value of lambda that we have here is indeed negative. So this is the way that I'm enforcing lambda being negative. I'm rewriting it as minus something that has to be positive because we're squaring it. Okay, so let's solve this differential equation. It has a characteristic equation. When we solve this, the characteristic equation will be m squared minus alpha squared equals 0. Right? So hopefully you're comfortable with this. We can jump straight from the form of the equation to the corresponding characteristic equation. This I can factor pretty easily. This is difference of squares, so I'm going to have m plus alpha times m minus alpha equals 0, which tells me that m is equal to plus or minus alpha. And so our solution is going to be that y equals c1 e to the alpha x plus c2 e to the negative alpha x. And there's what the solution looks like. But now again, we need to plug in those boundary conditions. So let's try y of 0 equals 0 and see what that gives us. When we plug in y of 0 equals 0, what I'm going to get is c1 times e to the 0 plus c2 times e to the 0 is 0. So there's 1. The second condition, y of L equals 0. Well, now I need to plug in L for the x position. So I've got c1 e to the alpha L plus c2 e to the negative alpha L. And that's got to be equal to 0. And now we try to figure out basically what this can tell us. So let's start with this one. This top equation here tells me I have C1 times 1 plus C2 times 1 equals 0. So this one gives me basically C1 plus C2 equals 0. Or alternatively, if I subtract 1 over to the other side, C1 and C2 are opposites. So C1 equals negative C2. Let's plug in this over here. So I'm going to basically replace C1 with negative C2. So this one is now negative C2 e to the alpha L plus C2 e to the negative alpha L, and that's got to be equal to 0. From here, I can factor out the C2 that shows up in both. So let me factor out a C2, and now I'm going to have negative e to the alpha L plus e to the negative alpha L, and have that that's supposed to be equal to 0. And the question is, what does this give me? Can I figure out what C2 is? Well, in this case, looking at what we've got here, I know that one of these terms, so ignore this minus sign here, e to the alpha L, e to any power is going to be a positive number. E to any power over here is also going to be a positive number, but one is negative, one is positive. So maybe it's possible that this term goes to 0. Is that a reasonable assumption? And the answer is no. It turns out that's impossible. It's impossible for this, regardless of the value of L that's used, regardless of, and it needs to work for any L. L has to be arbitrary, but also regardless for any alpha. We're never going to be able to get this term to be equal to 0, right? This is definitely not equal to 0. And the reason is I would need this to have the same power in both cases. E to the alpha L and e to the negative alpha L are obviously going to be different numbers, right? Just like if I did e squared and e to the negative 2, these are two different numbers. They're reciprocals of one another, in fact. So this number is the reciprocal of this number. The only time that they would ever be the same is if I got them both to be the number 1. But if the number was 1, that would mean that in that case, essentially, alpha would have to be 0. Okay, so let me try to reason through this a little bit more. Our goal is to see if it's possible to come up with a solution that doesn't force C2 to be 0. So our goal is it possible that this other term, the negative e to the alpha L plus e to the negative alpha L, is it possible that that part is 0, which would let C2 be whatever we want it to be in that case? But the answer is no. And we can check, basically, right? We can move this over to the other side, and we would have, in that case, if we tried to make this true, so if we tried to make negative e to the alpha L plus e to the negative alpha L equals 0, then I could add the negative 1 to both sides. We'd get e to the negative alpha L would have to be equal to e to the positive alpha L. I know that these two things are obviously reciprocals of one another. This would imply that e to the alpha L has to be equal to 1. That's the only way that this could work. But if e to the alpha L is 1, that means the power up here would have to be 0. So that would mean alpha L has to be equal to 0. We already know L can't be 0 because L is the length. So that would mean that alpha equals 0. But if alpha is 0, going back to the original equation, if alpha was equal to 0, well then I don't have a case where lambda is less than 0 because alpha, the relationship is right here. Lambda is equal to negative alpha squared. If alpha had to be 0, then lambda wouldn't be negative. Lambda would be 0. And we already took care of the lambda equals 0 case up here and found that we got a trivial result. So basically, assuming that this part of the equation is 0 leads to the assumption that alpha has to be 0. But if alpha is 0, we aren't actually dealing with this case. We're dealing with this case, which we already solved. So the short answer to all of this, to logicking our way through it, is what this implies is that C2 has to be 0. And if C1 is the negative of C2, if C2 is 0, then that means C1 is also 0. And between the two of these, again, we just simply get y equals 0. We get the trivial solution. Hopefully that makes some sense. So between the two of these, so far, both of them only had the trivial solution as a solution. So let's go to the last case. We've already tried lambda equals 0. We've tried lambda negative, so let's try lambda positive. So case number 3. What if we force lambda to be greater than 0? So I'm going to do the same thing we just did with that alpha trick. I'm going to rewrite my equation as y double prime, but this time plus alpha squared y equals 0. With again the same conditions, y of 0 equals 0, y of L equals 0, and again now lambda equals positive version of alpha squared instead of the negative version. Okay. This has a characteristic of, whoa. Let's see if I can get back to there. Okay. So what is the characteristic equation of this? It's going to be m squared plus alpha squared equals 0. And that tells me in this case, subtracting the alpha to the other side, right? This isn't a difference of squares, so I can't factor it that way. But this tells me that m squared equals negative alpha squared. Take the square root of both sides. This term is obviously has to be negative because this term is positive, but it has a negative sign in front of it. And this tells me that m has to be equal to plus or minus essentially I times alpha. And because it's purely imaginary, we get the case where we get only sines and cosines for our solutions. So in this case, the solution is going to be y equals c1 cosine of alpha x plus c2 sine of alpha x. And again, this just comes from the general form of these solutions that we did way back in section 4.3. Once we know the values of m, we can jump straight to the form of the solution. And in this case, here's what our solution looks like. We can plug in our conditions, so y of 0 equals 0, which implies when I plug in 0 for this, for x, I'm going to get c1 times the cosine of 0, so c1 cosine of 0 plus c2 times the sine of 0, and that's supposed to be equal to 0. This sine of 0 is already 0, so c2 can be anything according to this, but cosine of 0 is 1. So if this term is 0, this term is a 1, and this whole sum has to add up to 0, what does c1 have to be? c1 has to be equal to 0 in this particular case. So in this case, c1 is 0. That's what this has told us. When we look at the other condition, so now I'm plugging in y of L, and I found out that the c1 term had to be 0, right? Because this was a 1, but this was 0. So this term I don't even need to keep in mind anymore. I just can look at this other one. We've got c2 times the sine of L has to be equal to 0, right? So this was the term that survived. Basically, this term was gone, and not L, alpha L. I'm plugging it into this equation. This is the equation. We just determined c1 was 0, so this part is all gone. So here's what's left. I have c2 times the sine of alpha times the x value that we just picked. The x value we just picked was L, so I'm plugging in L. And that has to be equal to 0. Well, is it possible to find a non-trivial solution? Does c2 have to be 0, or is it possible that this can be 0? And the answer is yes, this can be 0. We don't have to force c2 to be 0. It's possible to find situations where this is equal to 0. So what this tells us is that c2 equals 0 or sine of alpha L equals 0. If I pick this combination of things, c1 and c2 both be 0, we'd get y equals 0, which is trivial, which is not what we want. But we found a possibility that allows for a non-trivial solution here. When is the sine function equal to 0? So if you remember your unit circle, sine is the y coordinate. It's 0 at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. As you go around this multiple times, as long as the angle, so sine of n pi equals 0. So as long as alpha L equals n pi, as long as alpha times L is any multiple of pi, we will have a solution here. That's basically the idea. So all we need to do is basically, again, figure out what is the value, in this case, of our alpha function, because L is prescribed. L is a distance. It's the length of the interval that we're dealing with. What does alpha have to be? Alpha is the thing that we introduced over here. Alpha is the quantity that's related to lambda. So is it possible to find a value of lambda which is related to a value of alpha that will make this true, where there's a non-trivial solution? Well, yes. All we need to do is divide both sides by L. We'll get n pi L for our value of alpha. And what is lambda, therefore? Lambda is equal to n pi over L squared. So this is what we're going to call the eigenvalue. It is the value of lambda for which there is a non-trivial solution. And the eigenfunction is going to be the solution itself at this particular value of lambda. And we already know what the solution looks like. It looks like this. We already killed off C1, so it's going to be basically the remaining term. So our eigenfunction is going to look like, and we can drop the C2 or leave it, it doesn't matter. Once you have one eigenfunction, any multiple of that eigenfunction is also an eigenfunction. But we've got sine of essentially our, where is it? Alpha x. So what was alpha? Alpha was n pi over L. So n pi x over L. So this is our eigenvalue. This is our eigenfunction. What was the point of this? And how is it going to work when you do these problems? Essentially, when it comes to eigenvalues and eigenfunctions, you're always going to start with this differential equation. But you may start with different boundary conditions than the one that I prescribed here. So on the homework, you'll have this differential equation, but with different boundary conditions. And you'll have to go through and try to figure out, for those given boundary conditions, is it possible to find non-trivial solutions? And most of the time, what you'll find is, in several of the cases, the answer is no. The only solution that works is zeros, right? The trivial solution. And we've already seen, right, the types of solutions we can get out of this are going to be exponentials, sines and cosines, or some products of both. Is it possible to find an exponential that goes through basically both of these 2 points? Turns out the answer is no. We couldn't do that. That was what happened here, right? Here were our exponentials, a positive exponential and a negative exponential. Could we force this function, the combination of a positive and negative exponential, to go through these 2 points? And it turns out the answer is no. We couldn't do that. In this case, it was a linear function, right? Our solution wound up being a line. Was it possible to find a line that goes through these 2 points that wasn't just the trivial solution? And the answer was no. Again, the only line that worked was y equals 0, the horizontal line, which is, again, a boring trivial solution. So in this case, we found a line and said, can we get a line to satisfy these 2 conditions? And the answer was yes, we could find one, but it was the only one we could find was the boring trivial solution. Then we said, okay, can we find a combination of 2 exponential functions that will go through those 2 points? And the answer was, again, no. The only way we can do it is by making these coefficients both be 0. And then the last one was, okay, could we find a sine or cosine function that can go through these 2 points? And the answer was yes. we're trying to basically force something that satisfies the differential equation to go through these 2 points, to go through 0 and L. Obviously, a cosine function isn't going to work because cosine functions basically start up here at a height of 1, right? So if we want to go through the origin, we can't use a cosine. The only way we're going to be able to make this work is by using a sine function, and that's exactly what we found out as part of our answer. The eigenfunction that we found was the sine function that happens to have the appropriate frequency such that it'll hit basically these 2 points. And in reality, the way that we found out is there's lots of different ones that'll work, right? If, again, looking at a sine function, I could have it go through, so if this is L and 0, we could have it go through, a sine function go through like this. Let's try that again. Close enough. Right, there's a sine function that goes through those 2 points. But I could also get a sine function that looks like this that goes through those 2 points, or a sine function that looks like this that goes through those 2 points, or one that goes like this that goes through those 2 points. All of those are possibilities, and they all correspond to different values of n, right? Basically, we just need to make sure our sine function's hitting these 2 points. We can do that with a low frequency or higher frequencies, and any function of this form is guaranteed to go through those 2 points. So that is the setup. And when we're trying to find these solutions, finding non-trivial solutions to differential equations of this form, those non-trivial solutions are called the eigenfunctions. And the essentially frequency, if you want to think about it, the value of lambda over here that will make that work is called the eigenvalue. And this will show up again. You'll see this a lot in linear algebra, and it always has to do in math. Eigenfunctions and eigenvalues are always when you're trying to find non-trivial solutions. They're always related to the idea of looking for non-trivial solutions. And so you'll see this again, and it's a cool thing. And these are the only problems from this section that you'll see on the homework. You won't see any of those bending problems. You won't see any of the electrical vibrations. You'll just see these eigenvalue and eigenfunction problems. And they're going to show up on the homework, and they're going to show up on the exam. So make sure you practice a few of these and make sure that you're comfortable with. Honestly, the hardest part of these is coming up with some of the logic to decide whether or not you can, and the algebra to decide whether or not you can find non-trivial solutions. What arguments can you make to say, no, this has to be C2 equals 0. Why can't this other piece be 0? So give it a shot, and just let me know if you run into any troubles on any of this.